SwayamPrabha. Digital India. Educated India.
Welcome back. We are going through this course of elements of solar energy conversion, and we are here at lecture 6. So, in first 5 lectures, what did you see? Let me just give you a quick recap of the topics. We have seen the basic concepts related to sun and earth, okay, and then we have looked at relationship between these two celestial bodies, between sun and earth, okay. Then we have looked at the characteristics of solar radiation, okay, and then we also looked at the concept of time, the solar time, standard time, etc. Okay, and then we finally what we looked at is the role of atmosphere in altering the solar radiation. Okay. So, these are the topics we have seen in first 5 lectures, and at the end of the 5th lecture we started talking about the prediction of solar radiation. We have seen why we need to predict it, because for any design purpose you have to know how much you will actually get, how much solar radiation you will actually get, how much of that can be converted, what would be the characteristic of that radiation, and all those things that you have to predict, right, and then only your design will be perfect and it will behave as you wish. Okay. So, that is why solar prediction is important, and there the most basic model that is often used, that is the linear model. So, what we do? We fit a straight line to the historical data to predict future availability of solar radiation. Okay. So, this we started looking at. So, the basic equation that we have used is this one. Okay. So, now we have to know or we have to understand what these different terms mean. Okay. So, these H that we have talked about, H means the global radiation intensity on a horizontal surface. So, H you can relate to horizontal surface, and that is why the symbol is taken. And whenever you see a bar on top, that means its average, and this particular average is most often done monthly. Okay. Over a period of month, we average the radiation values. Okay. Now, this let me go to the next page and explain what we mean by this SA bar. SA bar is nothing but monthly average of duration of actual sunshine hour. Okay. So, this actual term is the key point here, and that is why this A, the subscript A stands for actual. Okay. And sunshine hour, what do we mean by that? For how long sun is actually radiating, that is the sunshine hour. Okay. Similarly, this SP bar, this stands for monthly average of duration of possible, this P stands for possible sunshine hour. Okay. So, what do we mean by actual and what is meant by possible? Possible is what theoretically you can expect a particular point of interest will receive sunshine for. So, that is the possible length of sunshine hour. Okay. But actual is what you are actually getting. So, for a particular latitude and longitude, you can exactly determine for a clear sky all through what would be the possible sunshine hour. But in reality you will not get that because of many factors, like you have to take into the what is around that particular location. Okay. What is the altitude, what is the relative altitude with surrounding buildings, trees, anything else, because all of those things will actually tell you whether sun rays will be able to reach that location or not. Okay. So, that is why we distinguish between this actual and possible sunshine hour. Okay. Now, another thing I need to mention here, this subscript C. So, this subscript C stands for clear sky. Okay. So, whatever monthly average we are taking HC and bar, that is taken at the clear sky condition. So, that assumption is being represented through that subscript C. Okay. So, and okay. So, what is given and what we want to know. So, let me write that equation once again. Okay. So, here we have these two denominators, which is HC bar and SP bar, these two denominators are related to, or rather we obtain them from the historical data. Historical data, what do we mean by that? We have some observatories where we place these horizontal planes with some radiation measuring instrument, and we find out what is the total radiation that is being absorbed or being available to that particular plane throughout a day, and for each day for a very long time. So, that is a continuous process for all these observatories. We keep those data, and those are the data which are being used for calculating this HC bar and SP bar. Okay. Now, these two are available from the historical data. Now, what we want is this quantity, right? We want this is we want to know, or rather predict. Okay. Now, this quantity SA bar, that is what we measure for a particular location for which we are interested in. Okay. So, this is locally and temporally measured. Okay. So, on this basis we will actually get the H bar. And what are these? These are fitting parameters. Okay. And we will see that for different locations we will have different fitting parameters, and those are the space area or the location specific information that are there in those A prime and B prime. Okay. Now, one thing that we need to talk little bit about is that clear sky assumption. Clear sky assumption. How valid is that, or how useful is that rather? Valid does not mean much, but how useful? First of all, it will not be possible to obtain all those days in clear sky condition. Okay. So, difficult condition to satisfy. So, lot of data you have to discard just due to not a clear sky condition. Okay. So, that is not a good thing to have. And other thing is that even if it is clear sky, the other atmospheric variable such as your aerosol concentration, relative humidity, etc. These are not constant, right? Even if you do not have any sky, even if you do not have any cloud, then also you can have significant variability in terms of this aerosol concentration or relative humidity or some particular gas concentration. All those affect the H value or the energy received on a horizontal plane. That value is affected by all these things. So, clear sky is a dubious assumption to make. Okay. That is why later initially for long time this clear sky assumption data were maintained and used. Okay. But recently for past few decades we are using extraterrestrial value, okay, instead of clear sky value. Why do you use that extraterrestrial value? Because extraterrestrial thing is independent of anything that happens in the atmosphere. Okay. That is why you have a solid benchmark which will not change due to anything in the atmosphere, whether it is clear sky, whether aerosol concentration is more or less, it does not matter. That is why this extraterrestrial value is a much robust benchmark to calibrate everything against. Okay. So, the equation form does not change. What we change is, now we change that with the extraterrestrial value. Okay. So, now you can see this O stands for extraterrestrial. Okay. And also we name these coefficients differently. Okay. So, to distinguish from the clear sky coefficients, we drop the prime notation. Okay. So, A and B instead of A prime and B prime. Okay. You get it? So, now the equation form does not change, everything stays same. We only have taken out one of the key variable that can change the whole scenario. So, we have taken extraterrestrial value instead of clear sky value. Okay. And that way the A prime, B prime, they have changed to A and B. Okay. So, of course, again this A and B will be location specific, and the more the data you have, the better estimate you will get from this equation. So, more data will lead to better statistical estimation. Okay. So, this is the basic form. Now, one thing is that whenever we use this extraterrestrial thing, we have certain advantages as well. Now, both this H prime naught and S prime naught we can calculable exactly. Okay. We do not have to depend on data, but we can calculate it exactly. Of course, the more data you take, A and B coefficients will be much more stringent, because anyway whatever value you take in the denominator for extraterrestrial or clear sky assumption, the A and B coefficients, those coefficients will of course depend on the atmospheric condition and location, right. That is why we call it location specific. Okay. But now we have a better plane to stand on, where the H naught prime, H naught bar and SP bar, both of them we can calculate exactly. Now, we will see how we can calculate that. So, from earlier classes you have seen that the intensity on a normal plane in the extraterrestrial condition, that we can write exactly in terms of ION, which will be a function of the solar constant ISC and multiplied by this factor 1 plus 0.033 cos 360 n divided by 365. This we have seen earlier. So, please look back the earlier videos and you will find this particular equation. Okay. So, basically this ION is the intensity on a normal plane in extraterrestrial location, terrestrial location. Okay. And ISC is the solar constant, and you can see there is a variability which is taken from this taken by this cosine function. Okay. And n is the number of day which starts from January 1. Okay. Now, this is the intensity on a plane which is normal to the sun ray. Okay. Now, we are interested in a horizontal plane, right. So, let me write it to be OH. Okay. Here note the difference, this is H for horizontal. Okay. Now, how will this IOH be related to ION? This will be related to ION into cos of theta h. Okay. Theta h is the, you can say this is the angle of incidence on a horizontal plane. You can keep a horizontal plane in an extraterrestrial location, or you can like hypothetically keep it, and you can find what would be the angle of incidence on that horizontal plane, and the intensity will be just the ION, the normal intensity, multiplied by the cosine of that angle of incidence theta h. Okay. So, later maybe next class only we will see that this cos theta h we can estimate it exactly in terms of other angles. Okay. So, this is, we will derive it later, but for now you just accept that this cos theta h can be obtained exactly in terms of other angles. For now, please accept we know cos theta h exactly. Okay. Now, if that is the case, then what we can write, this IOH will now be ISC 1 plus 0.033 cos 360 n by 365, that will be multiplied by this cos theta h. Okay. Just do not bother about the cos theta h expression, what are those angles, we will go into detail in future classes. Okay. Now, once we know that, what we can find, this H naught is related to this IOH, right. What is that? H naught is nothing but integration of this whole IOH with the duration of sunshine hour. Okay. So, this is nothing but the integration of IOH over the period of availability of the sunshine. Okay. Because this is the daily value, daily value of energy received on a horizontal plane, right. So, this is just the integration throughout the day. Now, here we have introduced few new things without mentioning. So, let me just say that this omega s is nothing but the sunrise, or we can also call sunset hour, which is basically with respect to the solar noon when the sun rises or sets. Okay. Both of them are equal. If we consider the solar noon, then if the sun rises 5 hours from the solar noon, it will set after 5 hours from solar noon. Okay. So, that way this Ws, that is why this plus minus Ws, this covers the whole day. So, we said that H naught prime or H naught bar is exactly calculable. So, for that we need to know H naught exactly, right. So, to know H naught exactly, we need exact values of Ws. Okay. So, again we will show later, but right now let me just state them, how we get this, but we can state it now, that is this omega s is known in terms of cos omega s is equal to tan L tan delta. Okay. So, this is also known exactly for a particular case. Now, just to give you a idea, so what this omega s is, because otherwise you won't feel comfortable. So, we can say that if sun rises at 6 am and we are talking about solar time. Okay. So, with respect to the motion of the sun, if it crosses the horizon at 6 am, then this omega s is nothing but 12 minus 6, okay, multiplied by 15 degree, which is 90 degree. Okay. So, basically this is expressed in terms of angle. Okay. And so, basically time expressed in terms of angle, and when you have a gap of 6 hours from 12 noon to 6 am, 6 hours, and for each hour the sun traverses 15 degree. Okay. In 24 hours it traverses 360 degree. Of course, this is apparent motion. Okay. This I will not repeat every time, but by this time you have got the idea that sun traverses means the apparent motion of the sun. Actually the earth is rotating with respect to sun. Okay. So, that is how you get this Ws or omega s. Okay. Now, once we know that, then what we need to do? We need to take monthly average, right, monthly average of these H naught values. So, that is how you get this H naught bar. Now, there are two ways by which you can do this monthly averaging. One is take each day, find H naught for that day, then sum all of those days and divide it by the number of days. Okay. That is the most common way to do it, but there is one more like little sophisticated way to do it, is by defining an average day for each month. What do you mean by that? For suppose take the example of the month of January. Okay. So, for month of January you do the averaging by the first method, okay, and check which day of the month was actually the closest to the average value. Okay. So, you define that particular day, define the day which is having the closest value to the average, and that will be your average day of the month. Okay. So, and that way what you are doing, you are saving a lot of time. Every time you do not have to do the averaging for the whole month. What you do, you just find out the H naught for the average day. So, that way you reduce your workload very significantly. Okay. So, the average day has been found out with the help of lot of data throughout the world. Okay. Globally there are a lot of measurements and we have incorporated all of them, and for each month we have taken a average day. Okay. So, what are those average days? That is important to know. So, let me just write the average days. Okay. So, what we can write, so this is month and this is day number. Okay. So, for January it is 17th, for February it is 16, March 16, April 15, May 15, June 11, July 17, August 16, September 15, October 15, November 14 and December 10. Okay. These are the globally accepted values for the average day of the month, and correspondingly you can write what would be the value of n for those particular days. So, this is what you have seen, that this n appears in many of these equations that we are using. So, this n is the number of day in a year. So, January 17 is easy, n will be 17 because the n counting starts from January 1. Okay. So, for other, let me write the days because this will be quick reference for your computations. These are the values. Okay, this I made a mistake here. This will be 198. Okay. So, if we take these average values or average days of the month, then we are okay. We can reduce lot of data and workload by taking these single day that represents that month. That is how this H naught bar is calculated. Okay. Now, in the whole scheme of things, we have seen that how we can get the H naught bar exactly, but we also need to know how to get this particular SP bar exactly. Okay. So, how to get that? Okay. Now, actually for any day, SP you can write in terms of this omega s, which is the sunrise or sunset hour. Okay. And you multiply it by 2 because you have sunrise and sunset, and this 15 degree 15 is coming to make it in hour. Okay. So, as we know that what is the value of omega s, we can right okay. So, again we know this exactly. So, known exactly, that means now for monthly averaging we simply follow the averaging schemes as followed for H naught bar. Okay. So, after that it is straightforward. Okay. Now, one thing we can show you an example, not the calculation example, but how these data are maintained. Okay, let us say one location in India and that location is Visakhapatnam. Okay. Now, for that the latitude is known to be 17 degree north and longitude is known to be 43 degree 83 degree east. Okay. So, actually this is 17 degree and 43 minute and this is 83 degree 14 minute. Okay. So, these are the location of that or the latitude longitude of that location Visakhapatnam, and the elevation is also, of course, this is average elevation from the mean sea level, from mean sea level, that elevation is 3 meter. Okay. It is close to the coast. So, the average elevation is low 3 meter, and for that what we have calculated based on these curve fitting, this coefficient A is 0.28 and coefficient B is 0.47. Okay. So, these we calculate. Now, if we fit or if we use that equation, H bar divided by H naught bar equal to A plus B into S A bar divided by S P bar. In that equation, if we put these particular A and B, then we will get that equation will tell you the predictive model for the location Visakhapatnam. Okay. That is the way all the other places are also tabulated, and if you have something in between, suppose you have something in between Delhi and Kanpur, okay. Suppose you have data for these two places and you have to interpolate in between to get the value for that location. Okay. Now, another important question is that the total or often called global radiation. So, if this total or global radiation is predicted accurately, then how much of that will be direct and how much of that will be diffuse? This is an important question, right? You will understand or you will appreciate this even more when you will actually look at the concentrating solar collectors, because these concentrating solar collectors can handle only the direct sunlight. Direct sunlight means what? Which is coming from the sun without getting any change in direction, okay, without getting scattered. That is what it means, the direct sunlight. And the concentrating sunlight, the concentrating collectors can only take this direct sunlight, it cannot take the diffuse. But for non concentrating ones, collectors can take both diffuse and direct. It is not only the solar collector that distinguishes between this diffuse and direct sunlight, it also determine the heat load of a building, or how much radiation is available to a plant. So, this solar radiation data needs to be predicted for several purposes. Okay. So, for that, and also lighting. So, for the inside lighting of a building, if you want to use the solar energy, often we use only the diffuse part, not the direct part. Okay. So, for that also we need to have some idea whether it is diffuse or direct. Okay. So, now, so a fraction, of course, a fraction of the global value will be in diffuse form. Okay. So, what is that fraction? So, let us say diffuse is often designated as this H d, small d stands for diffuse. Okay. So, H d divided by H, okay, this is the diffuse fraction. Now, intuitively you can see that this diffuse fraction will decrease as the atmospheric scattering or presence of cloud increases, right? Oh, sorry, atmospheric scattering decreases or presence of cloud increases. Okay. So, basically we can relate this, that H d by H will decrease as H by H naught increase, right. H naught is extraterrestrial value. So, if you have cloud, then H by H naught will decrease, and in that case H d by H will increase, right. So, we define this particular thing, this H by H naught, to be a quantity called KT, or clearness index. Okay, clearness index tells you how much cloud or aerosol concentration is there. Okay. Now, you can estimate this again through lot of measurement, okay, estimated through location as well as climate type, specific measurements, and the accepted value for Indian condition. So, Indian climate, the accepted correlation is this H d bar divided by H bar. So, basically the average diffuse radiation fraction, that is 1.411 minus 1.696 kT bar. Okay. So, once you know kT, you can find this diffuse fraction. Okay. So, that is how the diffuse radiation is calculated. Now let me just write. Now, once we know the diffuse fraction, the complementary part is the direct fraction. Okay. That means this H direct is usually designated with capital D. This is 1 minus H. Okay. So, this is direct fraction and this is diffuse fraction, because this is direct plus diffuse gives you the total radiation or global radiation, right. So, that is how we get. So, these two important things we have seen. One is how to estimate the total global radiation on a horizontal plane, and then how much of that will be diffuse and how much of that will be direct, because some part will be useful by some particular device and the other part will be useful by other devices, and few can utilize both the diffuse and direct portions. Okay. Now, all these discussions can be, all these estimation or rather prediction discussions can be extended to hourly average values. What do we mean by hourly values? Because often we want to know for a particular day how the radiation is distributed for individual hours. Okay. It is not always that for the whole day we want to know the total radiation that is available. We often need to break it down into hourly values, and that is why we need this, and this we designate it with I. Okay. I can be confusing with intensity and the hourly values, but I designates the hourly average and H designates the daily average. Okay. So, this and then it is important to connect these two, how I and H will be connected. Okay. So, we connect this by a ratio of RT. RT, this represents the relationship between hourly global radiation and the daily global radiation. Okay, basically RT is nothing but I by H, and you can imagine that this will be a function of this hour as well as the total span of the sunshine hour for that whole day, WS. Okay, this gives the daily span and this gives the timing for that particular hour. Okay. So, now again this RT we can find out exactly, and we will see that in the next class how we can find it out, and that way we will be able to define or we will be able to predict the hourly values for each day for a particular location. So, we will see that in the next class. Thank you very much for your attention.